Okay, so in this class will be kind of independent, but I will use some of the examples and vocabulary we have built. And the idea is to introduce finally the concept of the basic concepts of category theory, starting from the definition. The intuition I want to have in mind about categories comes from this observation that I was saying the other day, something about like group theory. When you give me the definition of a group, I know what the objects you are studying are. I mean, you told me what a group is, but until the point that you have introduced how we get from one group to another, I have no idea what you're talking about. So I start understanding what your world of groups is the moment you give the definition of a homomorphism, and you say that this is the main way that you consider that we go from one group to another. So the nickname of a category will be something like mathematical worlds. Not always mathematical, but anyway. Okay, so one specific example, since I already mentioned it, would be the world of groups, which consists of the groups and the homomorphisms among groups. So let's start with this idea that in order to specify a category, I need to tell you what the objects are. Let's say I'm specifying a category, I will give it a name C, like this, and I have to tell you what the objects are. And I will use letters from this neighborhood of letters to denote objects. And I also have to tell you what the arrows are, and consider the arrows like the means of going from one object to another. And this is kind of confusing. Usually we pick letters from this, but I will tend to use lowercase letters for arrows and uppercase letters for objects, but forget any kind of intuition telling you like f is a function, or maybe telling you that a is a set. There's no requirement about the nature of the objects or the nature of the arrows. Obviously, I have some pictures that I can draw. This is where the names come from, like arrows and objects, and maybe a category looks like that, and maybe I should use some letters like this. There's something, yeah, okay, so this was bugging me. Okay. So if I have some objects A, B, C, and E, okay, there's another thing bugging me, there's no D, right? A, B, C, okay, let's fix that, D. And maybe these are like arrows like I, J, something like U, V, and maybe, I don't know, F and G. Okay, so this is how I would draw some objects and the arrows between them. So far, let's say I have specified what the objects are and what the arrows are. Obviously, I'm not done. I will need to have some kind of operation, some kind of interface, something of questions I can ask inside the category, and the category will be forced to give me some answers. I'm talking about operations here. And also there will have to be some kind of laws involved that have to be respected. You don't just get to draw something like that and say, okay, this is a category. So I will start writing in a way that it's not very maybe type theoretic, and it will gradually become more and more type theoretic. So consider that I have these two questions that I can ask on any arrow. So if the source, I will write it like that. If the source of f is A, and if the target of f is B, I can summarize this and write either this I know you want to think about functions, but resist the temptation. Or this. All those things will be synonyms. Okay, so if I know that the source of f is A and the target of f is B, I can summarize this writing this or that. Is that acceptable? I'm avoiding notations and names like nomenclature from category theory that's very dominant. I mean, source and target are quite common, but it's even more common to talk about domain and codomain. So you will also see this as domain. The reason I'm avoiding it now is that I think that if I start calling things domain and codomain, I will help you. I will encourage you to think that these are functions, and this is exactly what I don't want to do, because sometimes they might be functions or they might look like functions, other times they will look nothing like functions. So I think it's better to think of arrows, and I will refer to them as arrows, and say domain and codomain. Another nickname of something that maybe I should mention is that arrows are also called homomorphisms or just morphisms, and I will avoid these words for the same reason. Okay, so far I know that I can ask for each arrow for its source and its target. So it looks like this source and target business here have the following types. It looks like the type of source is, okay, so I will need notation for the objects, for the collection of the objects, and notation for the collection of the arrows. So I could write this like that, and I will use this a lot. Sorry, the other way around. So the objects of C is this collection. Consider this like some kind of implicit thing that forms collections, and the arrows is this collection. And another notation which is quite useful for the same thing is to call this thing. Where will I write this? Let's see. Okay, so I will refer to this as C0 and this as C1. And the intuition behind this notation has to do with the dimension of those things. So if you look at this picture, the objects are like zero-dimensional, while the arrows are like one-dimensional. Okay, so this is where this 0 and this 1 comes from. So if I write C0, just means the objects of the category C, and if I write C1, it's just a collection of arrows. So with this new notation that I introduced here, I can say like that the source goes from the arrows of a category to the objects of the category, and the target has this exact same type. So, okay. And if I take into account the fact that I can summarize this as that, it means that if I give you this picture and I ask you what the source, I don't know, like question like source of I, the answer is A, very nice. And if I ask you what the target of J is, the answer is A, okay? So from this picture, I can extract all the answers about these things. Make sense? Good. I'm not done yet. Let's say I have told you then what the objects of a category is. I have told you what the arrows are. For each arrow, I've told you from where it starts and where it ends. I'm not done yet because there are like two main operations, or like fancy operations, I don't know how you're going to call it, in each category, which says the identity. And the composition. Okay, so first about identity. The category has the obligation for each object I choose to tell me out of all possible, okay, I will draw some new sets here, sorry, some new arrows. That's not an arrow. Okay, let's call them, I don't know, X and Y. And let's call this that wasn't bad, X, Y, and let's call this P. Okay. So for each object I select, I can, sorry, let's see what's here. I get to ask for the category to give me the identity of this object. So this means that the identity goes from objects to arrows. Does that make sense as a meaningful question? What is the identity of B? And the category has to tell me, has to give me back a certain arrow. Okay. The composition, I would like to write, maybe, if I'm coming more from a set theoretic mindset, that's like you give me two arrows, and I will give back an arrow. This might satisfy, this way of writing, this might satisfy, I don't know, set theorist maybe, or someone more of Python programmer. I want to make it more specific. I don't want to say that I have a single composition, and soon I will do this for the identity as well. I want to parameterize composition and say that every time you have two consecutive arrows means a diagram like this. You have an operation parameterized by all these things, and now I can write a much better type here. Which will go from, okay, and it's time for notation. Good, okay. It will go from all the arrows. It will take arrows from B to C and from A to B, and it will give you back arrows from A to C. The difference in the order is because I'm writing composition in what's called like the algebraic order and not the diagrammatic order, but we'll switch between the two according to what's more convenient. So here I will say, and at the same time I'm introducing this notation. So it's like an arrow from B to C and an arrow from A to B, and it will give me back an arrow from A to C. And I will use the notation, this little ball, you know. Almost always I will leave implicit what are the parameters here. Essentially the parameters are just A, B, and C. The reason I'm using this is so that you don't have to keep in mind if I'm using diagrammatic or like algebraic order. And the other notation I will use, I think I've introduced it at some point, will be this, which is the same thing but written in the opposite way. So essentially, F and then G is defined to be G of or followed by F. This notation comes from programming languages. A lot of times it's like the separator of the statement, do this and then do that. So if you're looking at this diagram here, and you want to express the idea of this path going from A to B following this F here, and then this G. So you can either see it as first go through F and then go through G, or you can say that this path is the G of F. Hope this makes sense, okay? And now that I've done this, it seems like a good idea of, wait a minute, why should I not do something similar with the identity? So I will express the identity in a similar way, and this way will be, what is it here? I will parameterize the object, and I will say that for each object A, I don't need a diagram here, for each object A, I have, what is the type of id A? What, sorry? It's like, I've taken this, and I've passed it. I know why you said that, but it's not the case. Lazarus? Not A. Cannot really say A. What was your suggestion?
C, A, comma A.
Yes, I think both of you had this in mind, but the way you expressed it was not this idea. So like, the identity of A should be an arrow from A to A. And the identity from B should be an arrow, a specific arrow from B to B. So this gives me a way to express, to rule out a lot of junk, like the junk that I will mention right now. If I look at this picture now, and if I see these things expressed this way, I can spot some problems here. While if I was seeing things like this way, there is no reason to think there is a problem. Why is that? Okay. Can somebody spot a problem in this picture? Like why this will end up not being the diagram of a category? I want more ideas. Yes?
Καταρχάς δεν υπάρχει το δηλαδή άμα πάρουμε μόνο το διάγραμμα δεν υπάρχει το βελάκι από το α στο α.
Okay, you spotted something similar, I suppose, or a different thing? And something else. Okay, so first of all, Raphael says here that, look, there is a problem because I don't have an arrow from A to A. Okay, but if I look on this way that I formulated things, that doesn't seem to be a problem. Because you will say, what is the identity of A? Okay, maybe the identity of A is like this arrow here. And you'll want to pick up a fight with me, obviously. Why call it the identity of A? And you'll be right, but I need somehow to put this in the specification because until I do that, for all I care, maybe the identity of the thing that is called id A, maybe it's this arrow here. So this is prohibited exactly by this thing that Manuel has put there. And similarly, the composition of, like maybe somebody spotted a composition that's probably missing. So like if I do I and then G, there is something that goes from A to C, okay? But if I do, let's say, F and then V, there are no arrows from A to D. And the same thing, if I had left this thing like the original formulation composition, I would say maybe the composition of F and then V, maybe it's this arrow here. So I need to put these things down so that I don't have silly ways of expressing. So with these will be my official ways of specifying these things. I now can officially say that this is ruled out as a category because it has the obligation to speak one set from all those possible sets. So from all those possible, I will make this mistake a lot because in Portuguese the word for arrow is seta, so it was confusing. So like this, you may have a collection of arrows here from A to A, and the job of the identity is to tell you which of these will be selected and denominated as the identity of A, and like maybe it's this one, and the name of this would be, I will write this as id A, or also 1A. I will use both notations, okay? And what about the composition? You already know the notation I will use for composition. And also, since I will not have any other binary looking operation lying around, I can also write as juxtaposition this thing. So if I write GF, this means this, okay? So, okay, questions so far? So far I have told you all the data that somebody needs to provide in order for them to have a chance to have defined the category. It's like telling you that the group has like a binary operation, a unary operation, and a nullary operation, and stop there. So what I need to tell you is the equivalent of like laws, right? So it's not anything that has the correct types. So far, these are only types of things that gets to be a category. It needs to satisfy some laws, and luckily the laws are not much. It's one for the identity and one for the composition. Okay, so the law of the identity pretty much says that it deserves its name. But in order to speak of identity, I need to have an operation in mind, and the operation in mind is composition. So pretty much the first law tells you that the identity behaves the way you would expect from it, and I will express these things not as equalities, because we tend to use diagrams a lot, and we have met diagrams in the previous class. So there are two sides that an identity has to satisfy. It has to be, okay, it's better if I draw it and then explain it. Let's say we have any f, any f, no, I will say this, okay. This is the identity. I'm not sure what's the best way to do that, but the idea is that if you do this followed by any f, if you follow this path, first the identity and then any arrow to any other object B, this should be, and compose them, this should be the same way as just following f. So in order to express this as a commutativity of a diagram, I'll do it as a triangle. If I write it like that and tell you, hey, this thing commutes, right now I told you that if you do first the identity followed by any other arrow, it's the same thing as if you never did the identity and you just followed the arrow. Is that the commutativity of this diagram essentially tells you this equation, tells you that f of id is equal to f. Which id is that? It's the id of A, okay? And I need another one, which tells you that the other way around, I need it to be a left identity and a right identity. It's not technically a left and a right identity, the thing that I will write, because technically it's not the same id. But it's very convenient to think of it as some kind of polymorphic function, maybe. So this goes like this. Here I have another id. This is the id of B. And notice, please, that I don't need to write this. If I write id here, since it's from A to A, you know that it's this id I'm talking about. It could be no other id. And here I have the nef. And I will tell you that this commutes. And what I just told you is that, okay, I will use a different color here, like, I don't know, blue. I don't know, orange. And what I just told you here is that the id of f is equal to f. And this id here is B1. This is why I don't get to say literally that id is an identity for the composition, okay? Because these things are different. So, but any identity, if it makes sense on the right of an arrow, composed with an arrow, it will leave this arrow in place. It will not change the result. It's an identity. It's a right identity. Whenever it appears on the right, and whenever it appears on the left, it's a left identity. Okay. Okay, questions? Is it okay? Everything fine? Okay. So essentially, the only law I have so far tells me that identity deserves its name. And the other law that I will have is that composition is associative in the following sense. Again, I don't get literal to say that's associative because all the little balls that will appear there, these operation symbols, will be subscripted with different implicit types, but let's write it down. So the diagram here, in order to speak of associativity, I need three things, right? So in order to have three arrows, which are the things I'm composing, I need four objects. So I will write like that. A, then maybe B, then C, then D. So the idea is that anytime you have like this, let's call them, I don't know, F, G, H. Whether you want it or not, there is an arrow here. There might be more than one, but you know that one is guaranteed to be there, and you can ask for it. And this, you can call it GOF. That's how we call it. And you know that there is one here called HOG. Okay. So what you want? Okay. If I tell you that this diagram commutes, first of all, you can infer this and this. Big deal. You already knew that. So if I tell you that the two triangles commute here, I didn't tell you anything. Because if I tell you that this arrow commutes, what does that mean? It means that, literally, it means that G of F, I just described this path here, is equal to the other path, which is what? G of F. So it's like I told you, you know what? GOF is equal to GOF. It's valid, but it's completely trivial and meaningless. So it doesn't make sense to tell you, aha, this triangle has to commute and this triangle has to commute. But it was an exercise to check, like, if the cells of a diagram commute, the whole thing commutes. And it's a bit different now if I tell you, look, the whole thing commutes. Because if the whole thing commutes, maybe I should add these arrows to make it clearer. This arrow would be what? Would be the HOG, breathe, off, and this is like HO, breathe, GOF. Take a breath. Okay, so this is do this and then do the composition, and the other one do this composition first and then do H. And the idea is that these two paths should be the same. So if I write it down as an equation, this is that and why I'm saying that it's not literally associativity, although we will call it associativity of composition, because all these things, okay, not all, but we'll say, these things here have different subscripts, right? It's not the same. Let's try to write them down. So what's the subscript of the first one? This one. Suggestions. Do we get what I mean by the subscripts here of the compositions? It's this thing that I'm looking for, right? So how should I subscript this? Subscribe, maybe? Don't know. Yes?
BCD.
Let's see. Probably. Manolis is right because it's Manolis. So let's see. Yes, BCD, exactly. So this is parameterized by BCD. Oh, I said I will use this to not confuse myself, and I'm already breaking my rule. And what's the other ball? The second one, it's like the one that composes, let's see, this with this, so it's A, B, D, okay? And I will not do the rest. So this is like A, B, D. And similarly, these things are different, okay? So, but forgetting this small detail, we say that the second law is the associativity of the composition, and for the same reason, the first law is the law of identity, okay? Yes?
So I think I get why we want to parameterize the identity, but as for composition, wouldn't it be more reasonable to like not parameterize it and then add a law that says it behaves the way we want it to?
Why would you?
Stuff like this.
Okay, I said that literally what I said when I introduced is that some set theorists would like it the other way, and probably you are telling me I'm a set theorist right now. But like, why would you value more laws when you can have this information right inside your type? This is for the.
I want it to be the same operation there. Doesn't
But then it would not be an operation because it will have to be like a partial operation. Because what would be the composition of like if I compose f and this, I still would not get to call it an operation. I will have to drop totality of this operation, and it has to be partial, and I will have to say another law saying that it's defined if and only if the target of f is equal to the source of the next one, and I will have a bunch of laws, which I don't need here because the types guarantee that all those worries that you should have, you don't have anymore because they are inside the type. This is exactly the same reason why when I'm defining groups, I've given a definition of group as an example here, but like maybe you would expect him to see the silly law of it's closed under this operation. Like the first law is that it's closed under a group. This makes no sense from the point of view of if you understand what types are. This makes no sense because I'm saying that G has like these things. I don't know, and I'm telling you that the type of this. I'm telling the type of all of these. And from the first type alone, I already know that its type is this. So what is this extra law that you want to tell me that it's closed, that it's operation? It's an operation on G. And it means that if you give it two G's, it will give you back a G. So there's no way to say that. It makes sense to say closed under operation. We want to define what a subgroup is. Because you are in a bigger universe like a G, and you want to say this subset, is it a group? And you say, okay, is this subset closed under this operation? And then this makes sense, because you take two things here, and maybe, since whom are you asking to compose this, to operate on this two? The group. So maybe the product of these guys lies here. So it makes sense to say it's a subgroup if it's closed under all the operation. But it doesn't make sense to say that the first law of the groups is that it's closed under the operation. It's an operation of the group. How can it not be closed under this operation? So for the same reason, so it's like an information I already have on my type. Okay. So are we okay? So I think I'm done with the definition, happily, after like 54 minutes. Okay, no, sorry, it's not 54. I'm cheating, it's around 34 minutes or something. So this is what the definition, what the category is. Obviously, I want to give examples. But in order for you to come up and say, okay, I constructed a category, you need to be in position to answer in all of the following questions. What are the objects? What are the arrows? For each arrow, you have to tell me from which object it goes to what object it goes. For each object, you have to tell me out of all the collection of arrows that go out and go back inside the same object, which one you designate as the so-called identity. Finally, you have to tell me for each consecutive arrows, I will write this somewhere. Okay, so like you have an arrow for each diagram like this, out of all these arrows, which may be many, how do I call the collection of all these things? Somebody help me with the notation. The blue things, I have a name for their collection. What? CAB, okay, so this set, if you like, this is CAB. Thank you, CAC. So out of this, you have to select, like, okay, it's this one, to tell me what will be the designated as the composition of G of F. So this will be, and now you may think that, finally I'm done. He will leave me alone and he will accept that I have defined the category. Not yet, because all these things you have, these are the data, okay? So you give me all the data of what your supposed category is, you need to verify the laws. For the same reason that you don't get to pick a binary, unary, and nullary operation in a set and say you have a group. You have to do the work and prove that the laws of group are satisfied. So if you pick what you have to pick, I have to check that the designated identities behave like identities and the designated compositions leave the thing associative. Okay? Yes? So there is.
Do not think of CAC as a set, right?
Okay, I was hoping nobody would get there. You have some worries about size or something like that? Like it could be too big? Is that the thing or not?
Many questions.
Okay, if I switch from set to collection, are you okay?
No, I think we're just renaming it.
Okay, in many contexts, like set and collection are not like synonyms. Like when you study set theory, you say, okay, a set is a very specific object, it's on my table and I see it, and maybe you want to reserve the collection for like the outside perspective, the external, concept.
I was never convinced with this.
So that was not your objection. So what was your objection?
No, this is the objection, exactly. So how do you think of CAC? You think of it as a collection but not a set?
Yeah, think of it like the intuitive way, the external way of saying a collection of sets. And you may start having some problems if you think about sets, and if you fix a specific set theory, you may say, but there is no set of all those things because it could be too big or stuff like that. Let's not worry about like this kind of problems. They can show up if you worry about foundations in category theory, and you can solve these problems. But I mean, it's not the best thing to say, let's solve this problem in the first contact with category theory. For the same reason, you don't worry about this in the first time you see sets and unions and you start thinking about this way. A lot later, you start saying, what about, I don't know, Russell or something like that. So let's forget about the categorical Russell. Just rest assured that it can be fixed, but we should worry about it much later. If we go on with category theory, we can reach this kind of part, but we will not really need it. What I really need is a way to give definitions and notation that have to do with these things. So think of it a collection. A bunch of all these things, I want to give a name to these things, and the name I will give to them is this. Okay? Any other worries? Okay. So let's start with some examples. And the first example that I like to draw here is like, okay, this is a category. Try to prove me wrong. You understand what the object is? It's this dot right there. And what is so am I done? Have I told you like what the objects are? Yes, it only has one object, it's this one. Have I told you what the arrows are? I have drawn all of them, so it only has one arrow. Have I told you what the source and the target is? I've drawn it, but technically I didn't even have to do that, because since I only have one object, there is only one possible answer for both questions, what's the source and what's the target. It's the only object. Similarly, I don't need to tell you what the identity of this thing is. Technically I do, but it's for free, because I would have to select one of all these things. It's only one. So I'm done. So you need to check something. You need to check that the laws are valid. How could they not be? In order to break a law, you have to find some product that it makes a difference if you form it like that, or if you form it like that. But all products you can put here is like repeating this, going around this arrow a bunch of times. And since it's the only arrow around, I know, let's call this, I don't know, I. So I know that this thing is, I will write like that, an arrow from the bullet to the bullet. And I know that this thing is also an arrow from the bullet to the bullet. And I know there's only one arrow in my world. So I know they are equal. Does that make sense? So I don't really need... Sometimes when you draw things and you say these are the only things in the category, you essentially answer a lot of questions for free. Nobody can tell me, you didn't tell me how to compose. You know that the composition has to live here, and there is only one arrow, so I don't have to do anything. I would be in a serious trouble if there were no arrows for certain objects. Then I would have no way of making this a category. And It's also bad, but not as bad if I have many arrows. It's a bit bad because at least I have to tell you something. I don't get it for free. If it was only one arrow, I say, I will not even answer it, figure it out, it's only one arrow. If it's like that, so if I had like these two arrows here, I don't get to just draw this and tell you, you understand what category this is. You don't. Because I haven't told you, first of all, which of the two is the identity. I haven't told you what is this and what is this. And I have to define them in a way that it's associative, okay? But this is not the thing I'm trying to define here. I'm trying to define just our first example of a category, which is this, which what I will call one, okay? So this is a category, has one object, one arrow. It needs one arrow, it only has one arrow. It's called the category one. If you think it's trivial enough, you haven't met the next one. It's this one. It looks like that. I have already drawn it here. It has no objects and no arrows. Again, if you think it's not a category, find something that I broke. There are no existential laws it doesn't say there need to be something that does this. It's for any things like that, this thing happens. So I get away for free, define a category with no objects and no arrows. Yes?
Then you will add it as we did in the previous lesson.
You mean like if I can have an arithmetic on categories? I can. We will do that. But not yet. Quiz question, what should be the category 2? Okay, go ahead.
Two objects.
Let's call them ball and bullet and star, okay?
Yes, and all arrows between them.
First of all, you need one arrow here. You need one arrow here. The question is, do you want more arrows? These are called endo arrows. The arrows that have the same target and source. You need any more endo arrows? Which ones? No more endo arrows?
More endo arrows, it's pointless.
Okay, not exactly pointless, but it's not the thing you want to construct. Maybe some people would like to construct a different category, but the one you have in mind...
And then you have only two more arrows, right?
I don't know, you are constructing it.
Necessarily, because you can only go, yes.
So you want an arrow here, let's call it F.
Yes.
Do you want the other way around?
Yes.
Okay, Manolis doesn't like this maybe. Okay, first of all, it's not really a matter of if you need it or if you don't. Like, you can argue if this is if 2 is a good name for this one. And maybe Sotiris it's very good because it has 2 arrows. No, it actually has 3 arrows. And it has like 2 objects, and maybe you start saying which one deserves more the name. But it's a different thing, like if it is a category or not. In fact, the category 2 will be like this. And do I get for free to stop saying I have defined a category, or do I need to give you more answers? Like, do you know for each object which the identity is? Do you know for each composable arrows what is their composition? What are the composable arrows here? It's either this and then that. And I know that it has to be an arrow from the bullet to the star. So I already know the answer because I only have one arrow from the bullet to the star. And similarly, what is the composition of this and this? It's the only arrow that has the correct source and the correct target. It's F. So like if this is I and this is J, I already know that F of I is F, and I know that J of F is F. I know that because there is no space to choose to make any other choice here. But now, like to go back to the example of Sotiris, it happens that it's not what we call 2, but let's see if we can form this into a category and then have a break. Like I have a star here, I have an arrow here, let's call this F and let's call this G. This was the thing that Sotiris was describing, and the question is it a category or not? It's like, if you tell me that these are the only arrows there, first of all, have you left anything unspecified? Okay, you have these things as well, obviously. Do I get to complain about identities that they are not there, or that I don't know which they are? No, because the only objects are these 2, and each of them only has one arrow and the arrow, so I know what the identity is. Do I get to complain that you haven't told me what the compositions are? What is F and then G? I know it's an arrow from here to here, and since I only have one arrow, I consider this question answered as well. Similarly, I know what this is. And I need to check that they are associative, right? But if you look what's going on here, this is a special case of a category where all possible CABs are what is called subsingletons. And this is a good thing sometimes if you want to define. Subsingleton means that it's either a singleton or less, let's say. Okay, what does it mean? It has 1 or 0 elements. There's a technicality about this, why subsingleton is a better thing than disjunction. We'll discuss it later. But okay, here they are subsingletons, which means that I cannot break any laws. I cannot break the identity law, I cannot break the composition law, because the only way to break laws is if the answer should be a certain arrow and it's the wrong arrow. But if you're in a category where there are at most, between any two objects, there is at most one arrow, there is no way to violate any of the laws. In the worst case scenario is like there is no arrow, so you cannot, you should have an answer, you don't have an answer. But it's not possible to pick a wrong arrow. So this is a category, it's just not the category that we will call 2. So this is the category we will call 2, and it's a homework for you to think, not for now, let's see this on Zulip, what should the correct 3 and the correct n be, and we are having a break right now. Let's come back right around 10 minutes at most. Because
counting the arrows here, no?
we are just what? You think, not exactly, but you're trying to answer to this thing. Let's see this on Zulip, like what should be generalized and how. So break, okay, no break. Tell me.
Why do we need that?
We don't. It's not a. No, it's okay. It would be like the same question, like, okay, here's another category. You're right. So maybe your question should not be like why we need it. We don't. In the same sense, we don't need G there. We could define this one. This is another category, but it's not the one we call 2. Okay, this is like the discrete 2. If you want to give it a symbol, call it like that maybe. Okay, so it's yeah. But let's have a break. And okay, one more question. Yes.
Το identity ακριβώς δεν το ορίσαμε ως C of A to A, ας πούμε.
For any A, the identity of A, you know that it's of this type.
Ωραία, με αυτό το definition δεν μπορούμε να βάλουμε τα endo arrows και να πούμε ότι το identity...
Wait a minute, just I think, because you call the definition. It's not a definition, it's just its type. In order to tell you that I have defined, I have to tell you which of all the possible A to A's is the identity. Now I have defined it. This is the identity, okay?
Άρα δεν θα μπορούσαμε απλά να πούμε ότι το G of F είναι το identity.
Yes, if you exactly. You can infer this. So this was my point. Maybe it was not so clear. What is GOF? First of all, what is its type?
C of
It's first F and then G. So it's
bullet to bullet.
exactly bullet to bullet. So you could complain to like Sotiris, who was defining the like, you didn't tell me what is GOF. And Sotiris will tell you, you know it's from bullet to bullet. How many arrows are from bullet to bullet? 1. So you know that this is the same as the identity of the bullet.
So we can have a category without endo arrows.
No, because one of the laws of the category necessitates that for each identity, for each object, you need an identity. The way I've written it, it's not a law. It's already in the type of the identity. For each A, you need to specify the identity of A, so you cannot have a category without endo arrows. Okay, so break now, and let's come back after 7 minutes. Okay, so I have given so far the definition of what a category is, and some like important but maybe silly examples, which are like these 3. The category with only one object, the category with 2 objects and exactly 1 arrow between them and the obvious arrows, the category with no objects and therefore no arrows as well. And we also have seen this, I haven't given it a name, and I just told you what a sub-singleton is. It's the idea that something is okay, I will mention this to get it out of the way. So how do you say that something is a sub-singleton? What is the correct way to say it? Like the wrong way to say it is that it's either empty or a singleton. Because in the way we are looking at this, it means that if I want to prove that something is a sub-singleton, I need to tell you which of the two, right? And this might be difficult. Like, I could give you a silly example here. Okay, I will say what the correct way is. You say that this holds in it. This equation holds. Obviously, I'm talking about for all x's, epsilon, for all x and epsilon, y, sorry. This holds. This is the definition of a subsingleton. It includes the case that it's empty because in the empty, if your universe is empty, anything I write after a for all is trivially valid. And also if it has exactly one member. As soon as it has two distinct things, this fails, and this is what captures the idea of a subsingleton. The silly example would be like to consider, this is silly, I want to mention it, but it might get you to think about it. Like if I ask you to prove that something is a subsingleton, and I give you this set, all the x such that x is a least counterexample to your favorite conjecture of number theory. I don't know, like maybe the Collatz, or I don't know, Goldbach, I don't know what's your favorite one, so the Collatz conjecture. So, if you want to prove that this is empty or a singleton, you have to tell me if it's empty or a singleton and then prove it. And good luck with that. If you do that, congratulations. If you want to prove that it's a sub-singleton, it's quite trivial. Like, because you have to just prove that any two members of it are equal. So you start saying, give me two supposed members of this. So what do you know about these two members? That they are counterexamples to the Collatz, and what else? That they are least, and you know that the list is unique, so they are equal. Okay, so just to emphasize that it's not the same as saying this holds, or saying it's empty, or it's a singleton. Okay, so let's delete these things and go back to examples.
So this is basically a mean side effect of the fact that we don't necessarily assume lem.
Yes, exactly. If it's a lem, you could say, okay, it either is or it isn't, and you'll be done with it. Yes. So somebody asked in the break, like, what is the name of these things that are not constructive? People who like these things call them classical, and the rest non-classical. I will call the rest non-constructive and this constructive. Okay, I think it's like a pejorative term to say, this is non-classical. Okay, so let's go back to this. So I told you what a category is, and Raphael asked something very important, because like I was telling you that I don't know what you're talking about until you give me the definition of how you go from a group to a group. I don't know what group theory is. I know what a group is. The moment you say the homomorphs are this, I know what group theory is. And you asked me, like in the break, will we have something from a category to a category? If we don't, I don't get to say I'm doing category theory. Because I told you what the objects are, as categories of my interest here. I didn't tell you how we go from a category to a category. So until this point, you get the right to say, we have not seen what category theory is yet, what the world of categories is, exactly because I haven't introduced the idea of how you get from one to another. We could do it today. At the most, we will do it on the next class. It depends on how fast we go now. I need to give more examples. I mean, it's kind of interesting, before I tell you how you go from one island to the other, to just understand some different nature of islands. Yes?
On the question that Raphael kind of implied before, that can't we just have two objects and a function f and a function g? And
Please don't call them functions. And please correct me if I do that. I'll do this as well, okay? But go on. The arrows, yes?
To define the identities instead of as endomorphisms, as f to g arrows.
No, you would be violating the types of identities, because it's like maybe for Manolis he would rather say that this is an arrow, and then have a law that says, look, the source of how would this formulation go quickly here? So this is like how you would see it maybe in a different mindset. You would say, I need these laws. I need that I need that the source of id has to be A, I need that the target of feed A has to be A. I need that the source of fog has to be the source of G. I need that the target of fog, and so on and so forth, target of G. And I would, so like, you would have them as laws, some extra laws. I don't need these things the way I'm formulating it here because I have encapsulated all these things inside the information of the types. Yeah, I think it's okay. And if you want to deparameterize, so I have parameterized these arguments here. If you want to get them back here, the way to do that is through dependent types. So let me write this just to remember some notation I've been using. So I want to take this A and make it a proper argument. So I need to use the name here. That's the whole point. It takes an A of object. Remember, I'm denoting objects by C0. And then, taking an A, it gives you back what? Something of this type. And this is the dependency here of the dependent types, because this type depends on what the input was, not the domain, what the identity received. I think it's more, it's like easier on the eye, if you're not doing dependent type theory, to see it like that. You parameterize A, you hide this A here, and you consider have a family of A's. Or if you want to deparameterize it, you can see it as a dependent function. It takes an object A and gives back something of this type, from A to A. I need to speak of this A. And the same thing with this thing, with the composition, would be something like, I need to parameterize all those things now. So it would be like, you take an A B, and a C. All these are like objects. And we'll write it in a carried way. Take this, and then this, and then this, and after all this, you return, okay, I will write it here. After all this, you return what? You return something that goes from C, B, A, and BC, and C, A, B, to AC. So this is how you would write it as a dependent function. Sorry for the total mess here. It's this thing. It takes an A, an object A, an object B, and an object C, and then it gives you back something of this type. And notice that in this type, I get to refer on B, on A, and on C. Okay. But I don't think I think it's more readable to parameterize it the way I've parameterized it. Okay, so forget about this. So, further, yes?
I think that what he was asking is, like, if we have, like, for example, one of the groups above, we don't necessarily need to write out separately the arrows for identities because they could be implied by the fact that if we have an F that goes one way and a G that goes the other way, then if we have like no other arrows and stuff, the identity definitely has to be the composition of F and G, or something like that. If we allow arrows.
Okay, we have some conventions, right? We don't want to keep polluting our diagrams with like silly loops like this. I mean, since like for example, since the identity law mandates that for any object there is a certain identity, we never draw these arrows unless we want to emphasize something. So like if I would normally write the category 2 like that, and I told you I've given you all the arrows, and you tell where are these arrows? Okay, these are implicit. Okay, but the moment I do this. If I tell you I have given you all the arrows, it's fine. It means that you know that fog is the identity and that gof is the identity, okay? But if I tell you, okay, I have these arrows, generate a category out of it, this has to do with what's called the free construction of freely generated groups or freely generated lattices, or like, in this sense, you want like the most economical thing to be generated. But be careful here, because when you say the most economical thing, when you generate a group, out of some generators or a monoid or a category, when we say the most economical, we don't mean in terms of how many things it has in it. The most economical generated by F and G, it's this one actually, that only has these two. But it's not the one that's freely generated. The concept of free, maybe we'll see this like in a next, some other class, the concept of generating something freely, it means that it has the least obligations. It's economical in the sense of the equations that it has to satisfy. So if you tell me this, and if you understand that this is freely generated from this diagram, you're completely wrong, because you are saying that f of g of f is equal to f. And you are also saying that g of f of g is equal to g. And you are also saying that f of g of f of g is the identity. And you are giving here an infinite number of equations. So it's not economical at all. It's economical in the sense of how many elements there are there, but this is not at all what the word free refers to when you say freely generated by something. Does that make sense? Have you seen the idea of freely generated in groups, or who has ever seen groups, maybe, or not? Okay, so I'm trying to make a connection with something that doesn't even exist on... Okay, so now you know it. You know what freely generated means. It means like this has to be there, and all the things that are forced to be there should be there. Like if I want to start to generate a monoid out of an object M, what is the monoid generated by this weird M thing here? Let's call it, this is a symbol. What should I put there? And you look at the laws of monoids and you say, okay, there's an identity. And if you think that economical means as few things as possible, you say, okay, this is the monoid generated by M. It only has M, it's the identity, and M times M is equal to M, it's a monoid. And yes, it's a monoid, but it's not at all free, because M will complain there, say, why are you making me be the identity? Is there any reason that this equation needs to be satisfied? No. Okay, so you say, fair enough, I will not, let's respect the labor, I will not give you the job, so I will have to introduce an identity, because a monoid laws say that, okay, so how much is M times M? And you may say, okay, it's M. And then M will complain. Why do you say that I will need to satisfy this equation? Is there any monoid law that tells that this operation is like, as we say, what's the name of this thing? Idempotent, yes. If you want the freely generated idempotent monoid, then M will not complain, it has this obligation. But if you want the freely generated monoid, you want as few equations as possible. So what is the freely generated monoid out of one symbol? Essentially, can you see it? You have you have an identity thing, let's call it U, okay? You have M, of course. What else do you have? You have M squared, you have M cubed, and all these are distinct. Essentially, you are rediscovering the natural numbers with plus and zero. This is the monoid freely generated from a single thing. And this would be not strange, because this is how we have like successor, the successor of the successor, and we need an identity which would be the zero. Okay, I need to close this parenthesis now. I got carried away with the idea of freely generating stuff. Let's go back to seeing examples of categories, because we have seen so few examples, and not even the standard ones. I want to be a bit late on introducing the standard ones, exactly because I don't want you to think of functions and sets and stuff like that. So consider this category. The objects are the integers. I'm not saying it only has one object and this object is the set of integers. I'm saying that the objects are these guys. My -2, -1, tatatap, 42. These are the objects. Okay, so the arrows, here comes the tricky part. I will say that I need to tell you what this collection is from A to B. You know that A and B are integers because I told you that the objects are integers. So the arrows here would be, I will say the following. I have an arrow from A to B. Pick your thing, I don't know. It doesn't matter, it's something. If and only if A is less than or equal to B. So let's try to draw this and discuss it a bit. I will write like some objects here. So it means how many arrows do I have here? By the definition that I'm using, which is weird the first time you see it, it's like any two objects, between any two objects, I either have 0 arrows or exactly 1 arrow. So it's all the CABs are subsingletons. These things, one of the names of these categories are thin, for obvious reasons. And I will reserve the other nickname for these categories for a bit later. So I have these arrows here, I have this, what else do I have? Am I missing any arrows? Maybe. Yes. Oh, yes. So this is wrong. Thank you. Maybe I'm correct now. Maybe. I don't know. Do you get the idea? And you can ask me like, okay, you told me what the objects are, but what are the arrows? Like this arrow is what? Let's pretend that, I don't know, Manolis is really want to know what this arrow is. And the answer is, okay, it doesn't matter. This can be Manolis, okay? And maybe this can be something else. If I want to make an easy construction here, I could pick something that's easy to satisfy an answer, because soon I will run out of names, and I want them to be distinct, of course. So maybe I could say, okay, maybe this is the pair -2, 5. It's really, I don't care. Just think of it as a check mark. That's saying there is an arrow here. Okay, so the question is this a category? Are some things, first of all, my data, I said what the objects are, what the arrows are. Do I have all the answers to all possible questions? Have I said which are the identities? By the way I've defined it, there is a danger there, because I told you between any objects there is an arrow if and only if something, and I need to guarantee that these things exist here, because of this type. The identity of any A has to be an arrow from A to A, so all these things should have an arrow. I know that if they have an arrow, they have at most one, so I don't need to bother me to say which of these arrows is the identity, but I need to guarantee this. Why is this guaranteed? Yes?
Because the integer is almost equal to itself.
Yes, I have this thing, any integer satisfies this, and this means, by my definition, that I have an arrow there, and I have only one arrow there, so I have given this answer as well. Okay, what about the other possible danger? Yes? Wait, we are not yet in the laws.
Because you mentioned the one operation, so...
Yeah, but wait, I didn't mention the law of the identities. We are not in the laws yet. It's the type of the identities. So similarly, the danger would be with the type of the composition. Because if I'm composing like, if I'm doing this, and then this, out of all possible arrows of this direction, I need to pick one. I know I don't have a problem of making my mind, because if there is one, there's at most one. So this I get for free, but the danger is that maybe none. And maybe I have an arrow from here to there and from here to there, and this maybe is empty. What guarantees that this doesn't happen? Yes? Yes, the law that if you have this and this, you always have this in the integers with this relation. Manolis replied in a way that didn't give a hint as to the next thing that I want to define, because the first one he said x is less than or equal to x. He didn't say the name, and here he said the name, transitivity. Okay, so as you may start to figure out, there's not much thing special about the integers and the less than or equal to. So far, at least so far, we have used the reflexivity and transitivity of this relation. Maybe we can get a category out of any proset. We'll check it. But before we leave this example, Manolis still says, what about the laws? Because the types are there, okay, but what about the laws? What about the identity law? Again, since I am in a thin category, this means that at most an arrow, I cannot break any laws. Because the only way to break laws is to find a certain composition that should be equal to a certain arrow, and it ends up being equal to a different arrow. Since the source and targets are determined by the types I have, the only possible error here is if you get something like you composed F and G and it selected this arrow. You composed F and Goff and it selected this arrow, while if you compose Fog and H, it selected the other arrow. And these are not the same, so you have a problem. this cannot happen in a thin category because the source is fixed, the target is fixed from the types. I know that there is at most one, so I cannot choose the wrong one. So forget any, this is good. If you are in a thin category, you get for free the laws. You cannot break them. You still need to worry about the types, okay? So you still need to specify it in a way that they are there, but you don't need to care about making the wrong choice because you don't have any choice. That's the point. Not in the sense that you cannot pick one because it's not there, in the sense that it's only one, so don't worry about picking the right one. Okay, similarly, I could show like a different category. I will just change this thing into a different pre-order. I will use divides, and I will keep the objects, the integers still. So a different category would be, consider this ordered set, this proset, and get a category out of it. For exactly the same reason, I have identities. They are guaranteed by reflexivity of divides. And I have composition. It's guaranteed by transitivity. And why are the laws satisfied? Because by the way of defining this, it's again a sub-singleton, so it's a thin category. I don't even if I try to break any category law, I cannot. There is not enough room to break the laws. Okay, so let's make this into one of our first interesting constructions. How we get a category out of a proset. So this is a proset. And what are the objects? I need to say what the objects are. I need to say what the arrows are. And the idea is that the objects are the objects of my proset. I use this for carrier set, okay? And what are the arrows? It's the same thing. C, A, B. I will write it like that. This is quite common. If and only if A does this with B. Okay, so at this point, we see that any proset can be seen as a category. Okay, so in this sense, categories are generalizations of the idea of a proset. And one way to think about what's happening here, and I want to emphasize this a lot because it has a strong connection with proof relevance and how we go from saying things like, suppose, I don't know, A and B implies C, or saying things like, let H be an evidence of this thing. So the transition that goes from realizing that we should not only care if a proposition is valid or not, we should ask for a specific reason why it's valid and introduce it to our table so that we can say, we can do stuff with these things. So the same kind of shift is happening from the mentality when you go from proset to categories, because it's like saying that this is a Hasse diagram. How is it different from a category? Okay, in a category, maybe I have more than one ways to compare these objects. Let's call them A and B. This cannot happen in a proset. It's either less than or equal or it isn't. And you don't get to say, yeah, but, no, not again. Anticlimactic stuff, okay. That's a long beep. Okay, that's a new one.
It'll stop eventually.
Can you hear me?
Yeah.
Okay, yeah, fine.
It's not over.
It's not over? Oh, okay.
Κάποιος θα μιλήσει.
What, sorry?
Κάποιος θα μιλήσει, όχι. Το μεγάλο. Πλαπάτησε το κουμπί.
Okay, let's try to go on. Okay, so the idea is that in a proset, you don't get to ask the reason of why A is less than or equal to B. And if you say, I'm starting to have an interest in this, you reach the idea of a category this way. It's like categories like a proset where reasons matter. So you may have, forget it, okay, you may, it worked. You may have like 3 different reasons of why A compares to B in this way. And they're testing our patience. Yeah.
specific.
I think if they start calling like someone to remove the car, it will work much better than this. If they call like you should not, anyway, forget it.
Το επαναλαμβάνω κιόλας αυτό.
I hope that every beep was not an open parenthesis, and then we'll have to close all the beeps now. No, right? Okay. Okay. Luckily, no. Okay. So, let's see how reflexivity would work in this way. You have that in a Hasse diagram. You don't even draw this as a thing because you know it's there. But now, if you care about the reasons, you may have many things, and you say, "Wait a minute, about reflexivity, you have to tell me which one corresponds to the idea of reflexivity, which is the reason that didn't do anything, and this is why A is less than comparable to A." And the same way, when you compose things like that, like transitivity of the order guarantees that if you have A, B, C, D like that, and you have like A less than or equal, I don't need this. Transitivity is just that. A compares to B and B compares to C, but if you want to know the reasons why, this means that you need to add this idea of composition because you want to say, if I'm less than or equal to B for this reason, and I consider this reason next for B being equal to C, what is the reason from all the possible reasons that A is less than or equal to C that corresponds to the composition of these two reasons? So the simple transitivity of this gives rise to composition, and reflexivity of this gives rise to the idea of select an identity. It's like you put on your glasses. In the Hasse, you only see A is less than or equal to B, and now you want to see more, like what are the reasons. So, coming back from this, I have defined a construction on categories. It's not in the sense that give me categories and I will give you categories. It's give me a proset and I will give you a category. I will make it into a category. Okay, before I get to a similarly interesting construction, so we've seen here categories as a generalization of prosets. Now, just to confuse you, let's see a different category which is called proset. The important things in categories are the arrows, essentially. For some very bad cultural, whatever reason, social reason, many famous categories take their names out of the objects and not the arrows. So when you see something written like that in bold, usually the person is telling you what the objects are, which is unfortunate because many times in the same objects you want different arrows. Technically, they have to say all the information to be in a category. So the category called proset as objects has all prosets. And as arrows, can someone guess what are the way that we get from a proset to a proset? Yes?
Homomorphism.
What does homomorphism mean there? Yeah, so we call them either monotone or order preserving, all these things. Yeah, okay. So these are the preserving maps. Am I done? Maybe. I need to say, I'm not done actually. I need to say for any proset, this is a proset, I need to say for all possible order preserving maps, endomaps, I need to select which will be the identity. Which one do you think will be the identity? Yes?
The identity.
Yes, the identity, okay? So, do I get it for free? I need to prove something. So a lot of times, when you start studying set theory, you see some kind of exercises, prove this, and maybe you're wondering, what do I have to prove here? So in this sense, you need to prove that the identity function on a proset is really order preserving. Because who said that it's one of these things here? It ends up being, but this is something you need to prove. So once you prove that the identity on process is order preserving, and once you prove that composition respects monotonicity, respects order preservance, I don't know, you get to say that, okay, I'm fine with the existence of identities and the existence of compositions, and now I need to worry about like saying which one it will be, but it will be the composition and the identities, so you're okay. You have selected which things. Are they associative? You proved this in high school, in quotes, associativity of composition, because this is the composition you know, right? And does the identity behave as an identity for the composition? Yes, it does. You proved this as well. So these are things essentially one has to do in order to verify that this thing indeed is a category. Okay, similar thing, and I will not define it in detail. We don't have time for that, but you will get it. I can remove the R in process, and I will have poset. Like, I can have magma, I have semigroup, I can have monoid. The question is, what are, so these names, as I said, they take their names from the objects. What are the arrows? The homomorphisms, magma homomorphism, semigroup homomorphism, monoid homomorphism. I know all those things. So these are all categories whose objects are certain algebraic structures and whose arrows are certain homomorphisms between that. Not these two, okay, these are not algebraic, the rest are, okay. Abel, for example, would be what? You guessed it, abelian groups, okay, and what are the arrows? Homomorphisms between groups. I can have like topological spaces. What would be the arrows there? For anyone who has seen topology is like the study of continuous stuff, so the arrows there would be like continuous functions. Why are these categories? I need to prove stuff. I need to prove that the identity there is continuous. I've proved it in topology. I need to prove that composition is associative. I've proved it in high school. I need to prove that composition respects continuity. I've proved this in topology, okay? So all these things and a bunch of other similar categories, I will write them like that with bold-faced letters, and the idea is that you understand what the arrows are. It's unfortunate, because as we can see right now, like a very famous category, which usually is the first example, and for me it should not be, as I have demonstrated here, is set. And when you say the category of sets, the objects are sets, and the arrows are what? Yes? Functions. A much better name for this would be like fun for functions, or because it's fun. Because I could like say, let's consider sets and arrows. I want only injective functions. Is this a category? Let's see. Is the identity injective? Yes. Compositions respect injectivity? After some thought, yes. Or some proof in set theory, or in, I don't know, the first semester or something. Okay, so it's a different category. So like, this is why you don't get away to say the category of sets, unless you have like somehow agreed that when I say this, I mean that the arrows are functions. The arrows could very well be injective functions, or surjective functions, or bijections, or what have you. Or you have like fin sets, which is like the category of finite sets and arrows between them. And it's like homework for you to verify that these things are indeed categories. And I still have some time to introduce two more constructions. Very rapidly. Actually, I will take my time with the first one, and maybe I will not introduce the second one. I want to get a set out of a monoid. The idea is that the letter here indicates that this argument was a proset, while the letter here indicates that this is a monoid, but technically I need to say that. And now I want suggestions. Be careful. This category here is not this one. This is one proset that I'm looking at it as a category, okay? So it has how many objects? As many as this proset has, and how many categories are here? One for each proset, okay? This is one category, only one category. It has a tons of objects. Any proset is an object, and the arrows are the order preserving maps, okay? So don't confuse this, which is a certain process seen as a category with this, which is the category of all processes and all the preserving maps between them. For the same reason, don't confuse this thing that I'm introducing now, I haven't even introduced it yet, with this. This is the category of all monoids, okay? Here is, give me a monoid, your favorite monoid, and I want to look at it, to take a category out of it. Ideas of how I can do it. Think of a monoid first, like your favorite one, if you have a favorite monoid. Do you have a favorite monoid? We made a monoid in this, like...
The single element monoid.
Okay, this is a monoid, but it will not be very indicative. It's like, it's a trivial monoid. The same way you have a trivial group, one element group, you have a trivial monoid, just one element. Let's look at the other monoid, which was the monoid freely generated by a single object, which ended up being this monoid. This is a monoid, okay? Let's remember what monoid means. One law for each operation. It's associative, and the other thing is the identity, okay? How do I get a category out of it? Ideas. Let's do that, and let's be done with it. And this is a big shift that we need to take away from this idea that objects are sets and that arrows are functions. I mean, it's a very good example to break this whole idea. Yes?
I mean, with the successor,
No, it's not with a successor. The monoid has a binary operation and a nullary operation, and a constant. So the binary operation is plus, it's associative, and it has the identity 0, so this thing forms a monoid.
So plus.
It's a binary operation, just like a group, right? I'm mentioning group because I think you're more used to groups than monoids. But it's like, forget the inverses, and this is what a monoid is. And this is a monoid. It's not a group because we don't have inverses. If I change this to this, it becomes a group, if you like. And if I add the minus there. Okay, so, yeah.
I was thinking of the class. We have two branches and...
To design this way. No, Manolis. What are the objects?
The carrier set, the objects of the carrier set.
The object of the carrier set.
Yeah.
I will stop you right there. Okay. I would not stop you normally, but it's like we're all the time. It only has an object. What is the object? This happy guy. It doesn't matter which object it is. Pick up your favorite single object, bullet, star, whatever. What are the arrows? Well, I said that I'm going to get a category out of a monoid, so I have one arrow for each element of the monoid. So like this corresponds to 0 is this arrow, 1 is this arrow, 2 is this arrow. I'm done describing the object, it's this happy guy. I'm done describing the arrows, it's one for each element of the monoid. Question, is it a category? What do I need to verify? I've told you what the objects are, the arrows. I need to say what the identity is. So I'm not done. Because there is only one object, so at least I have to say what the identity, I have to pick one of these arrows to be the identity. Which one will I pick? Obviously. Or not so obviously, yes? The identity of the monoid, right? It happens to be 0 here. Okay, so I will single out, this is the identity of the happy guy. This is the identity of the happy guy is 0. And I have to say, for any two arrows that are composable, all of my arrows are composable, like one ends where the next one begins, I have to say, what is f of g? But remember, f is just an element of my monoid. Here my favorite monoid was a natural number, so this is a natural number. And this is an element of my monoid. So where do I send the composition? Which will be like the composition of 2 and 5? Will be 7, right? So I consult the only operation that I have from monoid, and I say, okay, this is defined to be f inside the monoid of G. What do I need to verify? The identity law. I need to verify that this behaves as an identity with this operation. Does it? That's the law, the first law of the monoid, the identity law of the monoid. And I also need to satisfy that verify that this is associative. This is the other law that I get for free from the monoid. So in this sense, it's a definite way to reach the idea of a category when you generalize from monoids. Like a monoid is a very special case of a category. You could define it that way. It's funny, usually category theorists like to give funny definition. I define a monoid to be what? A category with a single object. You'll never see this definition like in a monoid theory, probably. But essentially it's this. So in a way, you reach categories. If you like monoids, I can tell you, let's generalize this idea and let's introduce the possibility of having more bullets here, more objects, and more arrows. While what you're saying as a monoid is just if I focus on a single one and see all the arrows there. All the arrows, vice versa. If you pick any A and look at this forms a monoid. The identity is the identity, the composition, multiplication, or whatever you want to call it. So it's a good time to stop here. We have seen some constructions. I will just mention for you to figure out what will be the opposite construction for categories. If you so this is like a construction, a proper construction on categories. Give me a category. If I say the opposite of this one, you should understand what the category is. Just flip the arrows, this idea, and work the homework. So till soon on Zulip, I hope.